Hi guys, this is lesson 9.3. It's called Transformations of Quadratic Functions. And we're going to talk about what changes where the parabola is on the graph. I'm re-recording this because the first one, for some reason, turned out really weird and glitchy. So let's go through the examples again. So today we're talking about transformation. That's a vocabulary word. And the word transformation just means changes, basically. And so we're going to talk about the transformation of graphs. And specifically, we're going to talk about translations. And that just slides the graph around. It moves to the right or to the left. Or up or down. After we talk about translations, we're going to talk about dilations. And that's just when we multiply by something and we make the graph get wider or narrower. It changes the actual size. And then we're going to talk about reflections. And reflections are just like when you look in a mirror and something is completely reversed, or on the graph it's going to look like it is flipped. Okay, hopefully that'll make a little bit more sense as we look at the examples. All right, the first key concept is called vertical translations. So we're talking about something that will make our graph go up or down. We probably need to mention here in our regular vocabulary words that we're going to talk about parent graphs. And our parent graph in this situation, our parent graph is just something that is the simplest form of a graph. And in this case, we're going to talk about the f of x, or you could think about y instead of f of x, equals x squared. And that parent graph is super simple. It always lands right in the middle, and it has the same size, and it's a little smiling parabola just like that. So we're going to talk about things that change that parent graph. So when I have a vertical translation, I have something like this, f of x equals, and then here's my x squared, but I'm going to see something like this, plus k. And k is going to be a number. Now, if k is positive, that means we actually have plus k, then our graph is going to go up. If k is negative, then our graph is going to go down. Now, in all of these, basically you typically see something that looks like the opposite of what you think it should be. And the reason this one does not look like the opposite is it's already been changed. So in this case, we would have something like this. Let's call it y instead of f of x so it doesn't look too weird. Y minus k equals x squared. And so there would be the minus. If that makes it too hard to see that. Here, I'll just undo that. Notice that we have minus k on the left, and if I were to add k to both sides, I would get the form that I showed you here. And so they do that to get y by itself on the left, just to have this very sort of typical graphable equation where y is all by itself. But the effect is that we see plus k on the right instead of minus k. All the other ones that we see today are going to look like you have to translate them in the opposite of what you think. Okay, so here's an example of this. I would have something like this, the h of x equals x squared plus 3. and the effect that would have on the graphs. I'll put the parent graph in purple here. And I'm actually probably not necessarily being completely accurate on how wide this parabola is, so don't take that too incredibly literally. But plus 3 is actually going to make my parabola go up 3, 1, 2, 3, and it would look something like this. Exactly the same as that parent graph, so if I'm not drawing it as exactly the same, it's exactly the same. It has just gone up 3. All right, and then here's an example where we have kind of the opposite situation. I have let's call it the g of x equals x squared minus 4, and my original graph is a smile, and my new graph is down 1, 2, 3, 4. It's the same smile, only located down 4 instead. All right, key concept number 2. We're going to call this one horizontal translations. And we're going to talk about things that make our graph go right or left. What we're going to see is something like g of x equals, and this will be found inside the parentheses with the x minus h squared on the outside of the parentheses. That minus h is going to be, if we have a minus h like that, that is going to be a translation. We are going to move right. It looks like we should move left, but we're going to move right. And if we have this saying plus h, we're going to move left. It's the opposite of what it looks like it should be. So here's my example. I have the g of x equals x minus 2 squared, and that's going to look something like this. Here's my parent graph, and this whole thing is going to move to the right 2. So my new graph is going to look like this. The shape and size of the parabola doesn't change. It just moves to the right 2. Okay, the other example would look like this. Here's my parent graph. And I'm going to have something like the g of x equals x plus 1 squared. Notice that these changes are in the parentheses. And that's going to make me move sideways, this direction, left 1. All right, we can put these two things together. And we could have something like this. This is example 3. The g of x equals x minus 3 squared plus 2. And we've got both a left or a right and an up or a down. And so we're starting with our parent graph. It might look like something like this. And then we'll do this in 2 stages. Let's say we want to apply this next. That's going to go to the right 3. 1, 2, 3. And so if it was just only that change, it would look something like this. And then we're going to apply the plus 2. That means we're going to go up 2. And we're going to have a parabola, same shape and size still, but it's where the pink one is now. All right. We can also read that off of a graph if we're looking at a graph and do that, interpreting it there. I'm going to minimize my explanation here just a little bit. We're going to do an activity in Desmos that allows us to practice this. So this is basic information to set you up for that. Let's talk about key concept dilations. And for dilations, what's going to happen is we're going to have something like the g of x equals, we're going to have a number times our x squared. And so the key thing is to look at this number. And the funny thing about this is if a is a fraction or a decimal, okay, that means it's less than 1, then my graph is going to get fat. It's going to be compressed, is the technical way to say that. I like to just say it gets fat. It looks short. It looks like it's been sat on. Okay, if A is larger than 1, or a whole number, or anything more than 1, then it's going to get stretched. And it's going to get very skinny, narrow. Kind of like when you are playing with a little kid and they put up their arms because they want you to pick them up by their hands or their arms and swing them a little bit. They lift up their arms and then you lift up on their hands and they get really skinny and stretched out. Okay, here's an example. H of x equals 1/2 x squared. Here is our original parent graph. And what's going to happen is we're going to get fat. It's that one. It just gets wider, okay? And then here's the other situation. I have my regular parabola, and then I have something like this, the g of x equals 3x squared, and this one is going to get particularly narrow. So there you go. Now we can put these together with the other things, obviously, but I'm trying to keep us moving here. Okay, another key concept today is called reflection. And we're going to see this when we have the negative f of x, or basically where you're going to see it is right there. So the negative will flip our graph. It makes it frown. And so an example of that would be like this. We'll just do a simple example so you can see what that looks like. Here is my parent graph. And I'm going to do f of x equals negative x squared. And that's going to look like this. It just mirrors it right upside down. Okay, so those are our 4 translations, which takes us to the last concept of the day. When we see these changes, they often come in something called vertex form. And vertex form is awesome. It shows us a lot of information. It looks like this: f of x equals a, that's going to be the same as the a in ax squared plus bx plus c, times x minus h squared plus k. So we can see all of our changes here, but importantly, we can also see the vertex. And so the vertex in this equation, you can read it right out of the equation, is going to be at h. It's going to be your x number, and we're going to take it out as an opposite, and negative k. So I think I just said that backwards. We're going to take the opposite. Well, you know what? Let's say it like this. The vertex is at h and k, but you need to remember that the k is literal and that the h, you need to make it opposite. That's a little odd, but here, let me give you an equation and we can talk about the different pieces of this. If I have the j of x equals negative 2, this one seems to have pretty much every change. X minus 1 squared minus 2. I know a bunch of things here. I know the vertex, which is at 1. See how I read that? The minus is built in. And negative 2, that's where the vertex is. I know that this is a reflection because of the negative 2. It's going to frown. I know that this graph is stretched. That is how we describe the dilation, and it is going to look particularly skinny. I know, and that's all because of the negative 2. This is because of the negative 2. I know that it is going to go to the right 1. I know that because of the minus 1 there. It's going to slide that direction. I know that it is going to go down 2. I know that because of that minus 2. That tells me I'm going to go down 2, because we don't read that minus out as opposite. And so I could actually do quite a bit of graphing here just to think about this equation. Okay, remember that our original graph is just a plain parabola. And this one, let's see, we said our vertex is at 1 and negative 2. And that, see, the vertex kind of takes care of both the right 1 and the down 2, because you can see that it's already done that. It's gone to the right 1 and down 2. The vertex takes care of that. And then we are going to see that go upside down and be kind of skinny. So I'm going to kind of just show you that it might look like that, compared to my original parabola, which might have looked something like this. Okay. We're not going to work a whole bunch more examples on this recording. This will give you the notes, and then you can get some more practice in Alex and Desmos.